for this answer. So the question is, which is one of the main energy transformers of cells? What's our answer? Yeah. So our answer is A. This isn't a trick question. It's pretty straightforward. But I want to actually draw this and show you. So this is kind of like my reminder to do this for you. So this is our mitochondria. By the way, I don't know if you guys are aware, but mitochondria is plural form, so this is technically one, so it's mitochondria. And the way that this guy looks is we have this kind of situation. Now it's not, this has to totally be perfect or anything, but some kind of like wavy lines like this. Okay? And we have a couple different regions we need to label. So, this is the outer membrane. Again, membrane-bound organelles. Remember, those are the ones that the majority of your organelles are. So we have an outer membrane, and we have an inner membrane. But this one has a special name. What do we call it? Okay, so either one of those will do. And then what do we call this area? So it's in between the two membranes. What do we call it?
Inter.
So it is the intermembrane space. They're not deliberately trying to trick you with this. A lot of the names actually are intending to be helpful. So it's the intermembrane space, right? That makes sense. And then what do we call this area in the center?
Matrix.
Sometimes mitochondrial matrix, but we'll go with just matrix for here. Okay? So, it's really important when you're looking at cell respiration to understand where these things are happening, even if you're like having to redraw it to be able to visualize it. Any drawings that you can do for this exam are going to be really helpful to you. Any way that you can visualize it to understand what's going on. You guys saw a lot of the questions that she was doing with her practice were application questions. The way that you answer those is you take the knowledge that you have on this material and you have to actually apply it elsewhere. So you have to not just memorize something, you have to understand how it all connects. For instance, I do have a question I was going to follow up with, but I'll wait until we get to cell respiration so it'll make a little bit more sense. Okay, so any concerns there? Again, you want to know what the rest of these guys do, but you should be able to pull the definitions pretty easily. So I'm kind of skimming a lot of chapter 6 in order to get to the meatier stuff. But do let me know if you want me to define it for you. Okay? Alright, second one. Which of the following cellular structures is common to both prokaryotes and eukaryotes? So this is the classic, what is universal? Okay? So I'm going to just go ahead and write this. Universal structures, or any kind of cellular components. Alright? Let's think about this. Every cell, no matter what kind of cell, has a cell membrane. Right? Because we have to contain it somehow. They might have a cell wall, they might have other stuff, but every cell at least has a cell membrane. Every cell has cytoplasm. Again, that's the glue that holds all the stuff together. Every cell has DNA. Every cell has RNA. You guys will have a little bit more appreciation for that. I don't know if it's on our next exam or on the 4th exam, but it's coming. And the DNA stuff is actually pretty cool. So, hopefully you guys will have an appreciation for that. But again, it's like learning the process. So anyway, DNA and RNA are essential for the information that is going to basically tell your cells what to do. And then lastly, we need ribosomes. Because here's the deal, and we aren't there yet, but just to have you guys appreciate this, DNA is the original message of that you are, we turn that into RNA, and then we take that RNA to the ribosome where they make proteins. And the proteins are essentially, your arm, everything, it's all made of protein. So that's really what you are. So every organism that is considered living needs to have these things. What is not universal, the real difference here is that, I'll just go ahead and say this, prokaryotes do not have membrane bound organelles. That's really the key. Because ribosomes are considered an organelle. So that's a little bit of a sticky business here. But ribosomes do not have a membrane. Any organelle with a membrane is exclusive to eukaryotic organisms. Okay? So, what is our answer for number 2 then? A. So see, the questions are very simple once you make sure that you really know the information. Any concerns here? Okay. This is another one talking about different structures. So here we're going to kind of do a little investigative work. A cell has the following molecules and structures, and what could it be a cell from? That's what they're saying. So they have enzymes. Enzymes actually are also universal, but I didn't write them as structures. But again, what do you guys remember what enzymes do? Well, yeah, so primarily they accelerate the rate of a reaction.
Okay.
So once they break things down, if the reaction breaks them down, then yes, but not necessarily. But they do accelerate reactions. So enzymes are important for living things. So that's kind of universal as well. We're trying to see if there's anything that's specific to one thing. This is also universal, that's universal, that's universal. Okay? Yes, follow me there? But then we have mitochondria. And mitochondria are membrane-bound organelles, right? So, it cannot be a bacterium. It also can't be any kind of organism, because again, it can't be a bacterium. Is there anything that's going to decide if it's a plant or an animal? Yeah, this is the interesting thing. So, on both of those that you guys just mentioned, plants have a cell membrane or plasma membrane that is surrounded by a cell wall. So, everything has a membrane, it's just whether or not you have a cell wall. Plants do have a cell wall. So, if they said cell wall here, it would only be plants. And then on that other one, plants exclusively have chloroplasts, but everything has mitochondria that is a eukaryote in order to break down the energy. Because chloroplasts make sugars, but that doesn't mean that they can actually do anything with it. So that's kind of the interesting thing there. Yeah? Not 100%. Yeah, so the question was, are plants the only ones with cell walls? I guess we can make a little list here. Cell wall things. We have plants. I don't know to what extent you guys are going to need to know these, but we'll just throw it on here just in case. There's plants, there's fungi, and then there's prokaryotes. So animals are really the main ones that don't have cell walls. But yeah, so anyway, we could have a little bit more differentiation there. But this answer is going to have to be C. Because based on the information given, we don't know if it's plant or animal. Questions here? Okay. Now we're going to look at peroxisomes. Peroxisomes tend to give people a hard time. Sometimes we don't really know what's going on here. What chemical is primarily involved with them? Hydrogen peroxide, which is what gives them that name. You should make sure that you read it a little bit further, but if you see any question involving hydrogen peroxide, there's a pretty good chance you're looking at peroxisomes. That's kind of a little bit of a tip there. So I'm going to start actually, so it has these two different roles defined in your notes. I'm going to start with the second one, degradation, because it's a little bit simpler. It breaks down bacterial cell, that could be damaged organelles or ones that are scheduled for degradation. So anything that we don't want in the cell anymore for whatever reason. And this is actually similar to what organ? What does it sound like? It sounds
Lysosomes?
a lot like lysosomes, right? Yeah. So I'm going to mention this here.
So lysosomes.
But they do have one major difference. So, they produce H2O2, which is hydrogen peroxide. That is a product of their degradation. So that's, again, where they come up with this name. Hydrogen peroxide is actually toxic to any living organism. Like, scrape your knee, and it's like this giant gaping wound, and your mom drags you into the bathroom, pours the peroxide on it, and it bubbles up, and you scream because it hurts so bad. Well, anytime something hurts like that, it's because damage is happening. So, believe it or not, that is a toxic substance that was being poured on your knee. Now, the reason that you do that is because it's also toxic to, like, bacteria. So, they're a little bit more concerned about that. Although, in recent years, they've said it's better to wash with soap and water, but, you know, whatever the case may be. So, anyway, that's where you might be familiar with that. So, then you're thinking, okay, well, something with it. That's what the detoxification is involved with. Okay? The detoxification breaks down the hydrogen peroxide. I'm going to just sum it up. Okay? Because again, you don't want that in your cells. So, here's what this looks like. So we have H2O2, and it gets broken up into H2O and oxygen. For any of you chemistry buffs, this is not a balanced equation, and that's okay. We could balance it, but I'm not going to bother right now. It's just, you know, the numbers don't add up perfectly, but we can make them add up. The point that I'm trying to get at is that they break this down into water and oxygen, which are both non-harmful, right? So, that's why we say it's a detoxification process. Does that make sense? Yeah. Peroxisomes produce hydrogen peroxide. That's the only difference, is what they use to destroy foreign invaders. Lysosomes have their hydrolytic enzyme, but they don't have a very similar function. Yeah. Yes. Well, they produce it in their attempting to destroy things, but then, in order to keep you safe, they have to then break it down. Yeah, so it's kind of like they make this toxic waste that they then have to destroy, type of thing. Yeah? Yeah, lysosomes are organelles that, again, break down other unwanted things, but they use different enzymes for it. I don't think so. Yeah.
Is it 28?
So that's a very good question. Her question is, does detoxification only involve breaking down hydrogen peroxide, or could it involve other things? For peroxisomes, that's the only thing that they detoxify. But there could be other things that undergo a detoxification process. Just, you know, this is the one that we're looking at here. Alright, everyone good with this? By the way, this reaction is why when you add peroxide to living tissue, say when you put it on your cut leg, it bubbles. Because it's breaking down to produce water and oxygen. Yeah? Yeah, they don't degrade very as it may seem to be the case. But a phospholipid is simply a phosphate head, they call it. It's like the top of it. And then we have two fatty acid tails. Now, don't be fooled by the acid here. It's just fats. They just call them fatty acids for some reason. But it's very important to realize that this is an amphipathic, say that fast, molecule. Any of you guys remember what that means? Yeah, I like the overwhelming no, I also got. So this means that we have both polar and non-polar regions. Hopefully you guys are good with this from the first exam, but make sure that polar and hydrophilic are the same thing in your brain, okay? So we could also define this as they have both hydrophilic and hydrophobic regions, okay? I just wrote this because it's literally shorter, that's it. So this is going to be our polar, and this is our non-polar. Okay? We good with this? So this section will be hydrophilic, means it likes water. The bottom section is hydrophobic, means it doesn't like water. So because of this, they're going to have certain characteristics that they exhibit. So let's draw like a little section. Okay, so we're gonna make us some phospholipids. So it makes sense that on the one side, all of the polar sections are going to want to stick together, and the non-polar sections are going to want to stick together. But we call this a phospholipid bilayer, right? So let's make the second. All right. By the way, the tails can be either saturated or unsaturated fats, which is why, again, just for your knowledge, if you eat fish that is from colder water, it's healthier for you because they have more unsaturated fats. Because unsaturated fats freeze at a lower temperature. Yeah, interestingly enough. That's why like Alaskan salmon, they always say is so good for you. There is a little bit of truth to that, and not just pushing their standard agendas. So let's go ahead and relabel this again. So we have polar, we have polar, and we have this nice section of non-polar. Okay? And so when you look at this, this is actually, you have to imagine, a cell is a sphere, right? So this is like if we chopped it at a point, and we're looking at it on the side. So it's like this layer, and we're looking at just the side view. That's like a cross section. But if we can somehow get on top of this, then like maybe that's the outside and that's the inside, it would just look like a bunch of circles. You know what I mean? So they can all move around laterally. So laterally means like left and right. So like these guys can swap, these guys can swap. Because, all the polar stuff is together, all the non-polar is together. So it's this perfect setup where everyone's okay with everyone there around. But the polar doesn't want to interact with the non-polar. That's why they don't stack up two rows that look like the top one. You know what I mean? So, if you think about it, for this guy, if he wanted to flip and go up there, that's going to take a lot of work. Because this polar head is going to have to traverse this non-polar basically, to try and flip on the other side. So that's really, really rare. I had heard at one point, I think it's like, that might happen once per month in a cell of yours, which is a big deal. And then, flipping side to side happens almost constantly. Which is why they call it a fluid mosaic model. Because it's kind of like moving the whole time. It's not really stationary. And the reason it's a mosaic is because we have proteins that are embedded But that's kind of, we'll get there. So just try to have some appreciation for the fact that this is going to be relevant for everything else we do, including when we get to the end of cell respiration. Okay? So, I'm going to go back to the question. Oh, sorry. All right, let's go back to the question. Okay, so which of the following is a true statement about the three possible lipids? They can move laterally along the plane of the membrane. Again, sounds good, right? Because if they're moving left and right, the polar and nonpolar are staying in certain sections. They frequently flip-flop from one side of the membrane to the other. Again, like I was saying, that's the one that's quite a bit more rare, so that doesn't sound very good. They occur in an uninterrupted bilayer with membrane proteins restricted to the surface of the membrane. There's a couple issues here. The first one is that it says it's an uninterrupted bilayer, so it's just like solid, basically. And that's really not how that works. It's not solid at all. And then, if membrane proteins are only on the outside, you guys remember like carrier and channel proteins? What kind of proteins are those? You're like motioning. Do we have an name for that? Like integral membrane proteins, right? So if they're only on the surface, those are peripheral membrane proteins. So that one's no good. They have hydrophilic tails in the interior of the membrane. So that sounds tempting. But are the tails hydrophilic or hydrophobic? Hydrophobic. So be so careful. It's literally half of a word that invalidates this choice. Okay? Do not underestimate the power of reading every single letter of every single word. Okay? Don't just be like hydro, tail, interior, cool. Like check. Okay, they are free to depart from the membrane and go off on an adventure. No, not so much. Questions here? Okay. So, this next one is really interesting. In order for a protein to be an integral membrane protein, we just talked about this, right? So it's inside the membrane. It would have to be which of the following? So, let's go back to our picture. We're going to add more to it. If I want to put a protein in here, say I want to put a protein right here. Okay? And you got to assume that there's like more stuff happening on the side, but I didn't really leave a space for that. Okay, so this is an integral membrane protein, right? I'm going to label this. Do you think it stays there? Or does it like move around the whole time? So it's probably stationary, right? Like it's pretty solid in the membrane. So do you think it's polar or is it non-polar? Pretty close. Yeah, so I know you're getting the right thing. So it isn't really going to be helpful if it's only polar because then the middle section is going to be all wrong. And then it's not going to be helpful if it's only non-polar because it's going to be fighting the edges. So it actually has to be empathic. Empathic? That's something else. Yeah. So this actually has to be empathic. So it's like approximately that much is polar, that much is polar, and then that's non-polar. See what I mean? How like it has like these sections of it, so that way it can sit happily in the membrane. Okay? This is going to represent that. Okay? So just kind of translate those. If your heart so desires to draw the whole layer of phospholipids with proteins in it, by all means be my guest. It's just going to be a little bit of a challenge. Okay? So what I want to talk about first is when we're looking at diffusion. Let's go ahead and I guess down here we kind of talk about these things. So we have two different types. We have passive, we have active. And what this really boils down to is passive requires no energy, active requires energy. So the majority of the diffusion stuff we're going to look at is passive because it's way easier to do stuff if you don't need energy for it. So we have a lot more options for passive things. The first one is going to be simple diffusion. And this is no proteins. No proteins. Okay? So this is like, again, the simplest, most basic form of diffusion. The idea here is that some guy is just going to like sneak across this membrane. Okay? So when you decide what kind of molecule can sneak across, well, do you think it's going to be a small or a large molecule? Small. So that seems more intuitive. But would it be polar or non-polar? So what we're going to look at here is that a small non-polar molecule can easily pass through. And that's because you see how when we label the sides, there's such a huge continuous section of the non-polar because both tails are end to end, that if it can just get past the polar section, it's going to be easier for the non-polar things to pass through. So that's really one of the key things here. So we're going to look at small non-polar. That's all we need for simple diffusion. Okay? Our next option is going to be diffusion that involves proteins. What do we call that? Yeah. So that's going to be facilitated diffusion. Okay? So we have channel proteins and we have carrier proteins. So the question was, do they always use both, or is there one or the other? Normally, they'll only have one type of protein. So it's either going to be channel or carrier, but they're two of the same type, which is why I put them in the category together. So channel proteins is just there's a passageway available for a certain molecule. Okay? So I'm going to label this as passageway. Everything other than simple diffusion is specific for one type of thing. Okay, so just kind of keep that in mind in general. That's passageway. Carrier protein will actually escort molecules. It's kind of the easiest way to say that one. Okay? I actually have a good analogy for all of this, but I just want to get all the definitions down. For active transport, these require energy. So we're looking at usually some kind of electrogenic pumps. A good example of this is the sodium-potassium pump. And you don't need to know the specifics on that guy. But the idea is that these pumps are using ATP, or they're using some kind of energy. And they're almost always going against the concentration gradient. That's a really big thing you guys have heard over and over about this material is concentration gradients, right? So things naturally want to move from a higher to a lower concentration of themselves, right? And this is true for everything. If I let go of this pen, it's going to drop on the table, right? Everything wants to be at like a lower state or a more stable state. And that's really what's going to happen passively. Actively, we're going against, we're picking stuff up, we're moving things, we're putting work in. That's the idea. Okay? So, let me draw these. So, for some reason I always draw proteins like this. I don't really know why, because they're not like super nice. So this will be my channel protein. It won't be, this isn't going to be a simplification because we're going through protein. My protein is this blob thing here. Okay. Then we have the carrier protein, which is going to do some kind of thing like this. And there's like much better illustrations for you in your book, but I'm really horrible at this, so you're gonna have to bear with me. But it like goes into this chamber, and then the whole protein kind of like squishes it through. It's sort of like, this may not be a good analogy if you have no knowledge of like how the body works, but when you swallow food, you have these little things that stick out. You have these cilia in your throat that push the food down, which is why if you were, it probably would be comfortable, but if you were like hanging upside down for monkey bars, you could chew and swallow something, and it would still go to your stomach. You don't need gravity to do that. It's really interesting. Anyway, that's what I think of when I think of carrier proteins. And then we have another type, which are the pumps. And I'm going to just show this one going the other direction, because that's the best way to indicate that. Okay? So, yeah. Yeah. So that's a really good point. So the active transport stuff is very similar to either channel or carrier proteins, except for using the ATP. So that's kind of the major difference. So the way that I think about this is, think about a little kid, okay? So this is going to be, we're going to have like a child growing up through the years, trying to go on a slide, okay? So if you have this baby, and this baby is like 6 months old, like maybe, I don't know what that is. Maybe, the kid is like, I'm not totally sure developmental stages. Maybe, the kid will like sit up, hold his head up. If you're taking this child to playground, are you gonna like take them to the top of the slide and push them down and say, good luck, baby? Probably not, right? So in this case, what you're going to want to do is you're going to actually get on the slide first. You're going to put the kid on your lap, and you're going to slide down together. So did it require energy for you to slide down together? Well, like the actual slide, right? No, it doesn't require energy for you to do that. You're just carrying it along. So that's the carrier protein. That's the analogy there. Okay? So then, now we fast forward, he's like 4 years old. So now, they're able to go down the slide safely, unaccompanied. So that's like our channel protein. Okay? Just going down the slide again, up and down, right? Now, let's say they're like 8, and they're being negatively influenced by their peers at recess, and so they decide every time at the playground, going down the slide is so like last week, I'm going to climb up the slide and cause a bunch of problems. That would be active transport. down by themselves. So it's like you've created a passageway, they will use it, but it will just happen on its own. By the way, when we look at osmosis, when we do like the hypertonic, hypotonic, that's involved in channel protein. Does that make sense? Like how this all works out? Okay. So, let me put that back over there. Let's come back to the question now. Okay. So it looks like we went a long way just to get here, but there was a point. It was worth it. Okay. So which of the following is a characteristic feature of a carrier protein in a plasma membrane? Again, think. This is the baby. Okay. It works against diffusion. Yes or no? No, because that would what? Yeah, that's gas transport. That would require entropy. It exhibits a specificity for a particular type of molecule. You think so? Perhaps? So again, playground analogy. You're not going to just go pick up anyone's child and take them down the slide. That's going to be really tricky. So it's going to be the child that you were designated to supervise for whatever particular reason. It is a peripheral membrane protein. What do we think? So no, again, peripheral means what? On the outside. If it's only on the outside, is it going to be able to get through? No. So we can't do any kind of transport with peripheral protein. It requires the expenditure of cellular energy. No. Again, that goes along with choice A. It has few, if any, hydrophobic amino acids. What proteins are you required to know the amino acid makeup of? I told you not, right? So for this class, you never need to know anything like that. So that's definitely out. Okay? I'm not trying to freak you guys out. You do not need to know. Okay? That was what I was trying to get out of you. You guys are like, oh my god, which one's going to need to know? So our answer is B.
Yeah, I'm going to have it on these next songs.
Okay, so let's go ahead and take a look at this one. Okay, I think what our plan is going to be is we're going to finish this fusion stuff, and then we'll take a break and then launch into chapter 8. Okay? So we have a YouTube, and this is the fun time. I feel like that joke's made every semester, but I like to participate. The solutions of the two arms of this U-tube are separated by a membrane that is permeable to water and glucose, but not to sucrose. That is our golden ticket. That is our Simon Says. You need this information to proceed. Okay? Anytime you're dealing with a membrane, it's permeable to some stuff, but not to other stuff. Usually they're permeable to water. That's why we see the water moving, but not the solute, right? And now I've given you one that's ultra mega complicated, because if you can understand this, you should understand all of them, okay? Where in this one solute can move, one solute can't move, and water can move. So now you're just like all in a tizzy. So now we have to figure this out. It's actually not bad, okay? So we have side A filled with a solution of 2 molar sucrose and 1 molar glucose. Don't worry about the units. Just treat them as we have 2 units of this, 1 unit of this, okay? Side B is filled with 1 unit of sucrose, 2 units of glucose. Initially, the liquid levels on both sides are equal. Okay? So, what we need to do first is we need to look at what will happen with what solute can move. Okay? Which solute is capable of moving? It's glucose, but not sucrose, right? So, what order is the glucose going to want to move from low concentration to high concentration, or from high to low? High to low, right? So, we have 1 glucose over here, and we have 2 over there. So what's going to happen? It's going to want to move to the left, right? So we can actually, at what point does it stop moving to the left?
That's equal.
When it equals equilibrium, when it reaches equilibrium, right? So if we take the average of these to figure out what it would be to have them equal on each side, what's our magic number? 1.5. So we can actually do this.
To the left. Sucrose is going to the right, so it's going to be 1.5.
Good job. Everyone good? So we have 2 on one side, 1 on the other. Half a mole is going to move to that side, and then we're good.
These are going to be
Okay.
1.5.
So the glucose is equal. It's not going to want to move anymore because if it kept going to the left, then it's going to have a gradient to the right. You see what I mean? So it's going to just keep going
It
until
has
it's
to be
even,
equal
and
for
then it's done.
glucose to be
That's with
1.5.
anything. Again, it wants to get to the lowest level, and then it's done. So now that we've done this, what are we going to do with the sucrose? Nothing. Why? Can't move. We want to move it, but it can't move. So don't move it if it can't move. Okay? So now what we're going to do is
It
we're
says
going to add up
not
each
permeable.
side.
You can't get through the membrane.
What is, because the water doesn't care what stuff it is. It just wants to move where there's stuff. Okay? So, what is our total amount of stuff on the left side? We have 3.5 for both sugars together. Okay? On the right side, what's our total? 2.5. Okay, so now we need to see what will the water do. So actually, I'm going to use blue. I found this when I was working. I have this Hello Kitty pen that has lots of colors. That's really exciting. Okay, so then the question always becomes, what's the water going to do? So the water wants to go where there's more solute. The best way that I always remembered it, however you want to remember it is fine by you. But I always think about it like you're making soup, okay? And you realize that the soup is too salty. So do you want to take water out of it or put water into it to fix it? You want to put water into it to dilute it, right? So whatever side has more solute in it is just a really salty soup. And the water is trying to water it down wherever it goes. So it wants to go where there's more of the solute. Or again, you can think about it, the water is going from its highest concentration to its lowest. But whatever works for you. So in this case, is the water going to go left or right? The water is going to go to the left. My pen is like pretty weak, so that's okay. So the water is going to the left. So what's going to happen to the level of the water? So this side is going to move up. It's going to be much higher, right? And then this side is going to like come down here and be lower. Does that make sense? How we're doing this? So now let's look at the answer choices. Okay. After the system reaches equilibrium. So this means when everything is done. What changes are observed? The molarity of sucrose and glucose are equal on both sides. Yes or no? No. The molarity of glucose is higher inside A than inside B? No. The water level is unchanged? No. And then which side is the water higher? And that's how we do it. So that is like the hardest question you could possibly get. A couple other things just to analyze this real quick. Okay. Hyper versus hypo. Hyper means more, and we're always talking about the solute. Okay? So, I'm going to offer a recommendation now. The way that this works, actually, we'll go ahead and just make a problem real quick. So, let's say we have, I don't know, give me a number. How much solute do you want in the cell? I heard 30. 30% solute in cell. How much do you want out of the cell? 50. All right. 50% solute in solution. Sometimes you have a pond, sometimes you have whatever, but you have a solution inside is hypotonic in relation. So if you have one of those things where it's like this cell is creating and this cell is swelling, all you need to do is draw them, figure out where the water is going. Whichever one has more solute is hypertonic to the other. Okay? That's really, really super good. Yeah. The solution is hypertonic to the cell, which is hypotonic to the solution. In this case. Yeah. Isotonic is when they reach
Whichever
equilibrium.
has more
Exactly.
solute is
So,
hypotonic to the other.
and actually, just in case you get
Whichever
something
one
on
has
this,
more
the
solute is
water is
hypotonic
not
to the other one.
immobile. As in an isotonic
Just so I can
solution, it's
compare
not
to
good to say that the water is not moving,
when
but
compared
rather
to-
that there's no net movement. Because it can go in and out like a little bit. It's just not going to drastically go one way or the other. But exactly, that's when we're isotonic. Yes.
Think about it like
So, this is
we did before, like hyper,
go over here.
where it has more solid, has more sugar in the water.
Solution.
So if the cell has more sugar
The
than
cell
water,
has to be hypertonic.
and the water needs to go into the cell,
Everyone good with
then the
this?
cell's hypertonic.
I hope you guys are good.
Because
Make
that
sure
cell
you do
right
plenty
there
of
is
practice. It's
hypertonic
gonna be really
to
easy
the
questions today.
beaker
Worst
because
case scenario, you have a good
it has
50-50 shot.
less
So, I mean, it comes
solid
down to that.
than that
Yeah,
cell.
you have a question?
So the water would go inside the cell?
Well, we have more solute outside of the cell than inside, so the water's gonna leave. The water goes to where there's more solute. So the solution, the outside, is hypertonic. It has more solute. We're watering down the outside. We're trying to dilute it. That's the idea. One of you guys have a question over here? Yeah?
Yeah, here.
Yes, it's always a comparative situation. The solution is relatively hypertonic to the cell, and the cell is relatively hypotonic to the solution. That's our relationship. One, it's always like yin and yang. You know what I mean? Yes. Yeah, so, let me see. So, I'm just gonna, this is gonna be totally not organized, but I'm just gonna say turgid is, plant cell swelling. And then lysis occurs if an animal cell swells. The difference between the two is that a plant cell has a cell wall. So if the cell is super full of water, it's not going to explode. If it didn't have a cell wall, it wouldn't. If the cell wall is kind of like this protected box, it's like putting your stuff in bubble wrap. That's just using my allergies right now. An animal cell, however, if we put too much water in it, will explode because it just has a membrane. So we can definitely do that. And then we have for the opposite one of this guy will be placid, and the opposite of this guy will be prenation, or prenated, or whatever. I believe those are all of them. Do we have any more? Is that it, guys? I think that's it. Yeah. Okay. Good stuff. So just like be familiar with the terms. Normally, again, one side has only this one ion, one side has only this other one. So the second that we let it do its thing, they're going to want to start going to equilibrium, right? Things want to go high to low. So when they're naturally going from high to low, we're going to cash in on that energy. And that's basically the principle behind the electron transport chain. But anyway, the idea here is that we're creating some sort of potential energy that we can cash in on at some point later. Let's see. Let's take a look at these. This question tends to confuse people. Try not to dwell too much on the specific example, but get the idea of active transport out of it. It doesn't pump hydrogen ions. It actually pumps sodium and potassium, funny enough. And it forces them against their concentration gradient. So it means that if we have a lot of sodium on the outside of the cell, it puts more sodium outside of the cell, rather than letting it go in. It's like totally backwards from what would happen passively. That's why it's active transport. Okay? And again, the reason for this is because since it wants to get back so badly, then we can use that to power things for us. It's very, very similar to a hydroelectric plant where they create a dam in the river, okay? And they let the water through these very small channels, which then spin turbines to generate electricity. But we don't have to put work into that because the water naturally wants to flow that way. So that's how a lot of these processes are working, is we're kind of doing this sort of roundabout way to force things to naturally make energy for us. I hope I'm not losing everybody. But anyway, let's look at the rest of these. It does not ionize sodium and potassium atoms. They already exist as ions. Okay? It's used to drive the transport of other molecules against the concentration gradient. That is not the case for this, but that's how some active transport works. For instance, something that she used as an example in class, but she didn't require you guys to know, is that they will, when they bring glucose into cells, they actually put a phosphate group on it in order to get it to go inside the cell. Because you have, I don't know if I should go fully into this, but it's a way to get more glucose to go into your cell, even though you already have a bunch of glucose in your cell. We want the glucose in your cells, but naturally, if we let it just flow either direction, it would want to flow out. We don't want an equilibrium of glucose. We want to be able to eat it up. So we have to trick your body into doing these interesting things. So that is an option for some other ones, but not for this guy. And then the way that this works, again, this particular example, don't worry too much about, but it pumps 3 of these guys and 2 of these. And so since they both have positive charges, it's going to actually, by moving them across, it's going to make this huge charge difference, which again is going to be helpful later when we need to use that energy. So our answer is D. Yes. Yeah, they pump sodium out and potassium in, but the major takeaway, I really don't imagine you guys would get a question like this on here. I've been meaning to pull this one off because they used to focus more on sodium potassium pumps, but not so much anymore. But the key that I want you guys to get is that this is a classic example of active transport. Okay? Of the idea that we are trying to store this energy for use later. Alright, so the last of these we're doing some magic. So I'm gonna, well, actually I'll just bring down the other page later, but we have 2 more that apply to this list. So, and once we finish these, we'll take a break, okay? So hold on for just a moment. with the aid of aquaporin. What do we call this?
Yeah.
This is osmosis.
Automatically, you know how to do water.
Osmosis has to be water.
One of the key things here is water, but the rest of that definition is actually true. Okay? Our next one here, independent movement of small nonpolar molecules across the membrane. That's our simple diffusion, that's E. Okay? And then our last one, movement of solutes across a plasma membrane requiring the addition of energy. Active transport. I didn't put it on here, but if we were gonna do, let's see. Yeah, no, actually, I think it covers pretty well. Facilitated diffusion. We could have defined carrier versus channel protein, but I think you guys get the idea of that definition. So, anyway, we're gonna take about 5 minutes. Go ahead and just, be stressed and start. We're gonna be looking at some chapter 8 stuff. Okay? So, this question, which of the following is not characteristic of an exergon reaction? So, in order to look at this, we're going to draw a picture. So, we're gonna, you guys want to grab this paper again? Okay. Exergon. Okay? So, here's what we're gonna do. I want you guys to see this. We're gonna be able to talk about a few things with just one picture. So this is time. We've done this on that side, you guys have been there for that. Energy. So, okay. This is our reactants, and this is our products. Okay? Reactants are the start of the reaction, products are the end of the reaction. Okay? So, what we're looking at is a few things. We can say that from the start of the reaction to the end of the reaction, we have a value that we can look at. So, this value is going to be called delta G. Okay? So, delta G is the total, it's the change in energy of the reaction. The delta just means change. Okay? So, in this case, is it a positive or a negative delta G? So, if I put numbers here, and I say that this is at like energy level 2, okay, and then we go a few more, and this is like energy level 8. Okay? How we find the change, okay, if, I'm gonna do my model strip for you, okay? So this is our 0 point, okay? But I'm gonna start about 2 steps ahead, so we're gonna follow the course of this, okay? So I'm starting here, alright? So I'm gonna walk to the point where I'm at step 8, okay? So how many more steps am I gonna take? I'm gonna take 6 more steps. 1, 2, 3, 4, 5, 6. Okay? So in this case, I've gone positive 6 steps. I went from 2 to 8. Okay? However, that's not what we're looking at. We're looking at the final minus the initial. That's how we have to do this. Okay? So in this case, we have to actually take, so our delta G is going to be 2 minus 8. As we look at where we ended up, and then we subtract where we started. Okay? So we actually have a negative 6. Now, the numbers are going to be in negative delta G, so we were right. You just got to be confident in that answer. You guys see how this is negative? We end up with less energy than we started. So we've lost energy throughout the reaction, which actually makes it exergonic. So the way that you want to think about it is, if it loses energy, you're thinking, well, how can it be used to power stuff if now it has less energy? You might be thinking that. It's kind of a physics concept, but it's the idea of a system, okay? So it's like you can like make this little system in your hands. This is the reaction, okay? If it loses energy, something else had to get that energy. Ah, I like that sound. But I'm not gonna fully go there. Okay, let's everyone go with this delta G concept. Okay, so, something that's very important is that delta G will not change no matter what you do. So don't do it, okay? She will try to coerce you into saying that delta G can change. It does not matter what the situation is. We have an alien planet, blah, blah, blah. Does delta G change? No. We're going to follow our Earth system of delta G, which does not change. Okay? Because the reaction will always have the same progress. It'll always have the same energy at the start and the same energy at the end. Helium will always need these accelerators. In our example. Okay, so there's a couple other things that we need to look at here. The energy here, and that's from the energy of the reactants that we're starting at to the highest energy point. What do we call that?
EVA.
Anyone? This is activation energy, or energy of activation, or energy required to start a reaction, or energy required to get it going. Energy barrier, whatever you want to call it, is the hump that we need to get over. Okay, so it's kind of like a roller coaster. It always goes up and then it eventually goes down. We always have this because if you think about it, if there was no activation energy, Spontaneous does not necessarily mean like instantly or suddenly. Spontaneous means happens on its own. Maybe it takes like 3 years for this reaction to happen, but it will happen someday by itself. That is spontaneous. It's not nearly as exciting as like poof, and then it's done. So if we wanted to go faster, what would we do? Add an enzyme, yeah. Also, thank you for reminding me that. Enzymes are catalysts, so just make sure you're aware of that term as well. Okay, does it require a net input of energy? Ooh. Well, let's revisit. So here's the tricky bit. It requires input of energy, right? But does it require a net input of energy? No, because ultimately it loses energy. Net always means like the profit amount, or like what the result is after we factor everything in. So the net result is a negative energy. Yeah. Yeah, if it said, does it require does it require any energy at all? Like to begin, then we'd say yes, because that's the activation energy. But because we said net, that's our critical thing here. So it actually is not. And then what about activation energy? Is it relatively low? So here's the other thing. I actually didn't draw it, but we'll draw it real quick. Just so you have something to compare to. The endergonic looks like this. Okay? So the activation energy is this. And that's really, really big compared to that one. You see? And then the delta G here is positive. G. I kind of wrote it out. Yeah, the positive delta G, and it's a super high activation energy, which is why it requires an input of energy, and it's not supposed to. Huh? Exergonic reactions are spontaneous. Yeah. Okay. So, it's okay, you guys need pictures later. We gotta move on. We gotta go. Okay? Alright, so, exergonic reactions actually do have a low activation energy, so the net input of energy is the one that we're going to pick. We okay with this? Make sure that you know all these terms. Make sure you know catabolic versus anabolic, how those fit in. Exergonic reactions tend to be catabolic. Know which ones need ATP, which ones give ATP, which ones don't take. Great things. That's a great one. Can you break that one? Yeah, for sure. Okay, so this next question, we're just talking about how enzymes work. Do you guys have an idea for what the answer is? The answer is D. Do you see how the choices kind of start to mess with you if you're not totally sure of your answer? Because it's like, doing these different things. By the way, this answer choice
Means delta G changed.
that delta G changes, which is super no. But I just want you to realize that that's one of the ways they can do that. If they shift the equilibrium, that's changing delta G. Because it's the final minus the initial energy of the reaction. Okay. We go with that? easiest way to do it is to draw the pictures. We have competitive, inhibition, and we have competitive competes. Non-competitive is not. Alright, you guys got it, right? Move on. Anyway, so let me go ahead and draw this guy, and then we'll do this.
It's the tiniest little activation site.
Okay? What do enzymes act upon? Stuff? What's that stuff called? Starts with an S. Substrate. When I was in high school, I took AP biology, and we did like a Jeopardy game, and our final Jeopardy question was, what do enzymes act on? And I got the points and won that for a team. So I was a hero of the day. It was very exciting. So those are the substrate molecules. I'm like the coolest person ever, so don't be worried about it. Okay. So I'm gonna draw these guys, which are purple. And these are inhibitors. So the idea is that if the substrate is able to make it into this compartment, which we call the active site, by the way, because that's where the activity happens. If the substrate is able to make it to the active site, then the reaction is catalyzed by the enzyme. Okay? However, these inhibitors are also trying to get to the same spot. And if the inhibitor gets to the same spot, it's just going to block it. So that way, no more substrate can get it. So the enzyme is basically invalidated. Does that make sense? Okay. Non-competitive is a little bit different. That's a good question. The question was, is this like a long-term thing? Is it temporary? It depends on the enzyme, and it's a complicated thing. But it can vary. So there's different options. Is the quickest answer I gave you. Okay, so this one, let's say we still have our active site, right? And then let's say we have this other site. Okay? This is our enzyme again. We still have our substrate. But now, our inhibitors are going to be squares for our condition. So what's going to happen is these guys are going to go here, which is not the active site. Do you anyone know what this site is called?
Not active.
Allosteric site. That's all the shirt you guys need now, but we can so anyway, the non-competitive will bind here over on the side, which then is going to like warp this thing. So it's going to like twist it all out of shape. So that way these guys can't bind. So it's like the sneakiest thing ever. Instead of trying to block the same spot, it's just going to go in over here where the substrate's not even going to try to bind, and it's going to shut the whole thing down. So this one's a lot more effective than non-competitive. Yeah. Are all enzymes capable of non-competitive? Do they all have that allosteric site? It depends on the enzyme. Some have only one type of inhibitor, some have others. There's also mixed inhibition, which is really complicated. You get kind of into your later classes. But yeah, so I mean, there's some options for both. I wouldn't say universally every enzyme has both, but sometimes that is the case. Okay, we good with this? I just want to throw that in here, make sure you guys have a little tidbit on it. Okay. So, we're gonna go back to what we were talking about before. So, we have a reaction. There's letters. Do we care? I don't care. You shouldn't care either. The letters make no difference in my life. However, I am looking at delta G's. Okay? This one has a delta G of positive 3.2. What does that mean?
It needs 3.2.
Yeah, so it's an reaction, and it needs at least 3.2 energy. I'm not really putting units here, so we're just gonna put that. So it needs at least that much, okay? So the one who's giving the energy is always negative. Or if you want to remember it like this, although I'd be careful, you're pairing positive and negative, always. Here's the difference, is that this needs to be 3.2 or above in the negative direction, but it doesn't work the other way. I'll explain to you guys what this means. So on our answer choices, what's going to be the right one? C. Now if we had flipped this, okay? If we said a reaction has a delta G of negative 3.2, that means it can supply the energy for up to 3.2 units of energy. Positive. So you can have more of the negative than the positive, you can't have more of the positive than the negative. So it's like you can spend money and have money left over, but you can't go into debt. That's how this works. That makes sense? You guys are making no sounds, so, okay. All right. Yeah. Something I just said? Yeah. Oh, yeah, sorry. Okay, so again, it was if the question had said we have a negative 3.2 delta G, and then it's like what reaction can it supply? It can supply anything up to 3.2 positive. Okay. So the negative can always over do the positive. Yeah? Hang on, guys, I can't actually hear what he's saying. What was that?
Subtract 7.4 from 3.2. How did you get 3.2?
How'd you get 7.4?
I mean, how to get negative 3.5.
Okay. Thank you. It's really tough to hear across the room here. So, it doesn't, like, the fact that it's 3.5 doesn't matter. It just has to be anything 3.2 or greater in the negative direction. Is that good? Okay. Yeah. No, because if we have 3.5, so let's say it's money. If you have $3.50 to spend, and you find something that's $3.20, can you cover it? Yeah. Right. That's how much you're already gonna throw it out there no matter what. Okay? So it's a matter of can we cover the 3.2 colleges? Yes, we can. There will be a little bit extra, but that's fine. Yeah. If you're still kind of weird on it, then talk to me after. Alright, we gotta try to move on. We still have some respiration to do. We have like 20 minutes. Okay. Alright, well now we're here, so let's do this. Okay, so, and I just actually realized some girl came up and asked me a question. I gave the wrong answer because I gotta run and I gave the answer, so. Oh, shit. Okay, you know what, it happens. This is why I don't want to hold myself accountable. When we have 15 people here, we have 5 minutes. Okay, so I'm going to go ahead and write us the equation for cell respiration. Okay? So we have C6. That is glucose. This is your food. This is what you eat. Hopefully when you leave here, you're going to get yourself some glucose. That way you have energy, power for the rest of your evening. Yeah, you're just going to cook that up. I didn't eat one all day, so I'm cleaning up. And then we have oxygen. And this makes sense because you inhale, you breathe in oxygen, right? What do you exhale? CO2. See how this makes a lot of sense when you look at it like this? What else do we produce?
Energy.
And then, is there anything else? Yeah. of the following is not a byproduct? What does it mean to be a byproduct? This is a waste product or an unwanted product of some sort. Okay? So, here's the question. Is the heat energy a desired product? What do you want the heat for? Like, it sounds like a good idea, but think about, like, with your car, right? If your car gets however many miles per gallon, most cars get about 25% efficiency. That means that 75% of the money that you're spending on gas goes to heat. You don't like heat. Heat is not a good thing. Heat is definitely a byproduct. Because the heat isn't constructive, it's just there. And then we're like, alright, well, that was fun. It's carbon dioxide byproduct. Yeah, so that seems a little bit more intuitive. We exhale it, again, we spit it out of our cars. We run exactly the same as a motor vehicle. So it's an interesting thing to think about. This equation is the exact same for any fuel source. Like, if we could put like octane here, we get the same products. Except for ATP, because, you know, we're doing that in our bodies. Is ATP a byproduct? Probably not so much. What about water? It actually is a byproduct, so C is our answer. We want ATP. Yeah. Okay, guys. Bring it back down. Yeah. Yeah.
Wait, so what was the answer?
Okay,
ATP.
so yeah, we can definitely talk about that. So, let me write this. So you may have different ways that you remember this. I'm gonna teach you my way. Leo the lion says bird.
Lose an electron, oxidation, gain an electron,
You lose
reduction.
electrons. You are oxidized. And you can't say oxidation because that's vague. So it's the same thing with like the hypertonic, hypotonic, where one happens, the other happens. If something's oxidized, something else is produced. So we have that same trade-off. So whatever lost electrons is oxidized. And then if you gain electrons, you get reduced.
There's like a tiny mention of redox reactions in our slides. That's what this says. Redox, oxidation, reduction, oxidation. Someone asked her what is being reduced and what is being oxidized in the cellular respiration.
You can also mention hydrogen. Okay, they're relatively synonymous. So what we're looking at is we're comparing glucose to carbon dioxide because they both have carbon. And then we're comparing oxygen to water. So we're going from this one to this one, and we're going from that one to that one. So does this one gain peroxidizing this piece. You're oxidizing glucose. We're not gaining elements. We're gaining a subatomic particle. So, sort of, we're gaining components of an element, but it's not considered because it's only the electrons. But it does make sense to me that what is an element that will be, yeah. Okay, are we okay? Alright. And 12 minutes. We're gonna do the best that we can. So, where does glycolysis occur?
Cytoplasm.
This is in the cytoplasm or cytosol, if you want to call it that. Cytosol or cytoplasm, I don't know. Like that. Okay, so we're going to put an input and an output. This is going to be very similar to the chart that Professor Thomas made for you. This is just how it makes sense in my brain. Okay? And we're going to actually track what happens to everything. Okay? So we're not just going to leave them hanging, this just happens. We're actually going to explain why this is happening. Okay? So in the input, we're putting in a glucose molecule. You always want to think about that overall cell respiration equation that we did, because any input will always come from the inputs here. Or it will, all of the inputs will be sourced either from the first half of this reaction or from the output of another one. You'll see what I'm saying. So we're starting with glucose because it's on the reactant side. Okay? And then what are we producing?
ATP
So we
and
made
AH.
2 pyruvate. Now, we're actually going to look at the carbons here. Glucose has 6 carbons. And now, some of this that I'm doing for you guys is slightly beyond what you need for this exam, but I want you to understand it, not just memorize it, okay? So just kind of bear with me on this. If it totally makes no sense, just go strictly with the notes and go for it. Okay? Each pyruvate has 3 carbons. So that makes sense. Glycolysis is literally splitting of glucose, glycolysis. Okay? That's our entire process. What else do we produce? So we produce NADH, and we produce ATP. But here's the deal. 2 ATP are required, and 4 ATP are produced. So, classic question comes up in every course that ever talks about cell respiration, including this one. If you're talking about how many total ATP are produced, your answer is 4. Total. However, how many net ATP are produced? 2. If you use 2 but get 4, you really only get 2. Like overall. So again, we talked about this in SI, but it's like if I give you $5 and then you give me $10, did I really make $10? No, I only made $5. That's the idea. We only made 2 ATP in profit. So net versus total is a critical difference. Make sure you read every word. But it's a very easy one to get right as long as you read it, and then you're fine. Okay? That's everything glycolysis. Now, what was your question? Your number? Okay, so her question is glycolysis catabolic or anabolic? She was getting the idea here is that the first half of glycolysis is anabolic. That's why we need the 2 ATP. The first 5 steps of glycolysis, which someday, if you're about to
In
major,
the
you will actually
intermediates, the
really call
pyruvates being oxidized.
fun stuff. That requires the energy. We're building things up to a higher energy level.
That's why we need NAD to come along,
So the second half is
because that's the oxidizing agent. Because NAD is reduced, takes the electron, and that's how you end up with acetyl.
Why should that be able to text us? How I don't know, like, I know.
Yeah, so the input you could put that is NAD plus, but I'm not putting that because the
Are you guys taking
NADs
chemistry?
are already, the NAD plus is already in the cell.
So you know like the
So
oxidation
it's
rate
kind of
on
implied that that would be there. We can also put ATP plus heat as input, and then, you know, ATP ends up being our output. But it's sort of redundant to do that. So I'm actually omitting those things just for clarity. But technically, yes, that is there. Does anything I just said make sense? Yes, these are the things that are like coming out of the world into this reaction. So, again, we can analyze every single step of this. We take in glucose, where does that come from? Food, right? We take in 2 ATP, where did that come from? That came from probably previous cell respiration reactions, okay? We get the 2-pyruvate. Where are those going to go? Well, they're going to go to our second step, which the intermediate step, as I've written it here, is kind of like just in between these two. Sometimes it's lumped in with the Krebs cycle, but I'm keeping it separate. It doesn't really matter too much. But we're actually going to move these down here. So we've taken care of the pyruvate. What happens to the ATP that we made? Yeah, the ATP are free. You're done. We made them. Goodbye. Okay? So they're going to go do things like maybe power more glycolysis, but they might not. They might do other stuff. Okay? So the ATP are going to go do ATP-related activities. What are the NADHs going to do?
they're gonna go to electron transport chains.
These are going to go to the electron transport chain. We're making a giant circle. Okay? And we'll talk about why that is the case, but for right now, just take my word for it. Okay? So everything is accounted for from glycolysis. Agreed? Okay, so this one, we take in pyruvate. We also need oxygen. Where does oxygen come from? You breathe it, right? You take that in. What do we, and remember these are the 3 carbons, okay? What do we produce? Well, what does pyruvate become? These become acetyl-CoA. If you ever look at coenzyme, and it's going to like blow your mind. So you think it's this little tiny thing, but really the coenzyme A is this huge molecule, and then the acetyl is 2 carbons. So it's very funny looking. But this is 2 carbons each, okay? So if we're doing our math here with the carbons, we lost 2 of the carbons. Where did they go? We lose them as CO2. This is why I'm doing this. Professor Thomas won't necessarily make you track every CO2, but I want you to because then you know where your carbons are going. I want you to know where your stuff is going and actually understand it, okay? Okay, so then, is there anything else I've made here? It's not officially glycolysis or the Krebs cycle. Depending on what text you look at, sometimes it's glycolysis, sometimes it's Krebs. I'm just putting it as its own thing, but it's not, you're not going to be asked where do you classify the pyruvate to acetyl-CoA step. Okay, and we also produce 2 NADHs. Where are the NADHs going to go?
Electron
Straight to
transport
the electron
chain.
transport chain. You see how we're doing this? So I'm going to add them to our shuttle system. Into the Krebs cycle. Where does the acetyl-CoA go? Yeah? It's just in, yeah. So the coenzyme A, the CoA, is just in the cell. Again, it's one of those things. So we have this acetyl-CoA. We're also going to bring in some oxygen. Okay? Every step here is going to require oxygen except for glycolysis. We call this anaerobic, which is a big deal. It's the only one that doesn't use oxygen. So, you know, it also is the only one that doesn't use mitochondria. So if you need to do anything without the mitochondria, we're good there. Where does the Krebs cycle happen?
In the matrix.
Tim and Tom, it just has to do with transporting the okay, so here's my cool mnemonic for remembering the Krebs cycle products, okay? Here's what we do. 1, 2, 3, 1. 1 ATP, 2 CO2, 3 NADH,
on its
The
right.
ATP is going to go and it's going to do ATP things. Again, remember, this is what's going on here. The CO2, what do we do with that? We exhale it, that's waste. What do we do with the NADH and NADH2? These are going to join to the ETC. See how everything we're keeping count of now? Now, we are here. Where does the ETC happen? Where?
Kristen?
Well, in the crystic, or the inner membrane, depending on how you want to put it. It occurs on either side of the membrane, but specifically around that membrane. Okay? What are we starting with here? What have we been bringing here? NADH. FADH2. I'm going to let you guys know we're at 6:29. If you have somewhere to be right at 6:30, then you can leave at that point. But if it's okay, I'm going to continue just for a couple minutes. We shouldn't go more than 2 minutes. Okay? We're also bringing oxygen again. Okay? So here's the deal with the NADH and the FADH2. Okay? We have, I'm actually going to jump down here before I do this. We have NAD+, okay? And somehow it becomes NADH. What I want you guys to realize is that, and this is going to sound weird, but just bear with me, a hydrogen atom is composed of 2 things, okay? It has 1 proton and 1 electron. That's it. If we put a proton and an electron together, no matter where they came from, we make hydrogen. Okay? So, we have an extra proton here on the NAD+, right? If we just add an electron, we get to the NADH. That is why this is called an electron carrier. Its entire purpose is to carry electrons to the electron transport chain. See how this all fits together now? So, let's take a look. So we made ATP here, right? How many do we make? Yeah, so we're going to go with 34. They keep changing the numbers, but it's a lot of ATP. They can't decide how many. What else do we make?
Water.
We make water. Okay? So, let's answer this question real quick, and then I'm going to draw it for you, so that way you can see. Okay? What is the purpose of electron carriers NADH and FADH2? Transport electrons out of mitochondria? Out of mitochondria? Read every single word, guys. Every single word. Of every choice. To deliver electrons to the electron transport chain. That sounds pretty good. Well, let's just check. To create water by delivering electrons to oxygen. That does happen, but that's not the point. That's the key. That is not the purpose. Okay? Or to neutralize charge by removing electrons. No. Okay? So the answer is B. If you guys have to run now, you can go, but I'm going to draw out the electron transport chain process. Okay. That way it's easier to learn. I can strongly be
circle the
For the record, is an enzyme. We have some issues with that in SIO. Anything with ASE is an enzyme. Oops, I don't know what just happened. I hit a button. Okay. So, alright, we have the AT synthase, we have all of these other things. Remember, the NADH and the FADH are showing up to bring their electrons. So we have NADH, which is going to become NAD plus, okay? And then it brings the electrons. Okay? And then the same thing is going to happen with the FADH. I'm just going to draw it with this guy. So first off, I want to mention this NAD plus that we produce is going to go back to the other processes because now the bus is empty, right? So now it's going to go pick up more passengers. It's going to go to glycolysis. It's going to go to the Krebs cycle, and then it's going to pick up electrons over there and then bring them back here again. It just loops over and over. Okay? That's the NAD plus. That's what they do. So electrons show up here. They're going bounce along. Now, the difference between what I'm telling you and what you're told in class is that you're told just hydrogen. I'm just telling you a little more, okay? It's actually electrons on the electron transport chain right here. Electrons, okay? So they're jumping across. Because of their jumping across, we have protons, okay? Protons are symbolized as H plus because, again, a hydrogen atom is only a proton and an electron. So if we take the electron away from hydrogen, we end up with H plus or just a proton with it. Okay? So the movement of these electrons creates something called proton motive force. What this means is that it's going to force these up from this side of the membrane to that side of the membrane. We have protons just lying around, and they are going to get shoved through. Okay? So the electrons go this way, protons go this way. Now the story starts to get a little bit more familiar. We have protons that are building up, right? Because we're forcing them through. But again, this is kind of the thing where this would be active transport with the protons if it wasn't for the fact that the electrons were powering them. So the electrons are kind of like the water, forcing this situation to happen, but we're actually going to get energy from it because normally this wouldn't want to happen. Okay? And so we have this enzyme here, and this is like our dam. Okay? So now we know that the protons want to go from a high concentration to a low concentration. The higher concentration is at the top, so they're going to want to flow naturally back down here. This is where the ATP is made. The way that it's made, when I say it's made, it's not actually that the molecules are officially assembled. It's that we have ADP and then phosphate, okay? And they're just waiting to be put together. They're like, oh man, I hope something comes through here and gives us the energy to connect. And then they get that energy and then they connect. So that's actually from what you were asking earlier. Yeah, so in a lot of these cases when we say we're making stuff, what we're really doing is we're just putting together separate pieces that are already there. The ADP and the P are already in your cell waiting. So we're going to smash them together to make the ATP. ADP is just one less phosphate, but it doesn't have nearly as much energy. So ATP is the high energy one. Okay? So then we have to clean up the mess that we made. Because now we have the protons